Greetings to everyone. The topic of our video today pertains to a groundbreaking discovery in quantum physics. The first direct observation of a superradiant phase transition, a phenomenon once thought unattainable due to theoretical constraints. Scientists at Rice University have unlocked this exotic quantum state in a crystal of erbium, iron, and oxygen, revealing new possibilities for quantum computing, sensing, and communication. By coupling the magnetic fluctuations of iron and erbium ions, they bypassed a long-standing limitation, creating a magnonic version of SRPT. This milestone not only confirms a 50-year-old prediction, but also paves the way for next-generation quantum technologies with enhanced precision and performance. Without further delay, let us delve into our discussion. Astonishing, scientists have unveiled a quantum marvel, long deemed a mere theoretical dream, shattering barriers in our understanding of the subatomic realm. At Rice University, a team of intrepid researchers has captured the first glimpse of a peculiar quantum event predicted over 50 years ago that could transform quantum computing, communication, and sensing. This phenomenon, known as the superradiant phase transition, emerges when two sets of quantum particles synchronize their fluctuations without external prompting, forging a novel state of matter. Their findings, published in Science Advances, describe experiments with a crystal of erbium, iron, and oxygen, chilled to a frigid -457 degrees Fahrenheit and subjected to a magnetic field reaching 7 Tesla, over 100,000 times mightier than Earth's own magnetic pull. What is spin, you ask? Imagine it as a tiny compass needle tethered to each particle, electrons or others, ceaselessly spinning, pointing in a definite direction. When these spins align, they weave magnetic tapestries across a material. Ripples in this pattern, like waves across a tranquil pond, give rise to collective excitations called Magnons. Originally, SRPT was envisioned as a dance between quantum vacuum fluctuations, elusive light fields that flicker even in empty space, and matter's own oscillations. Yet, in this study, the team orchestrated the transition by entwining two magnetic subsystems: the spin fluctuations of iron ions and those of erbium ions within the crystal. Here, iron's magnons take the stage traditionally reserved for vacuum fluctuations, while erbium's spins embody matter's restless dance. For decades, skeptics doubted SRPT's existence, citing a no-go theorem in theoretical physics that thwarts such transitions in light-based systems. Undeterred, the researchers sidestepped this hurdle by staging a magnonic SRPT in a magnetic crystal, leveraging interactions between two spin subsystems. With cutting-edge spectroscopic tools, they detected telltale signs. One spin mode's energy signal vanished, while another displayed a distinct shift, a kink, clear as a footprint in fresh snow. These spectral markers align perfectly with theoretical predictions, affirming the team's success in summoning this elusive state. We forged an ultra-strong bond between these spin systems, witnessing an SRPT that defies past experimental limits. This triumph isn't just a nod to a half-century-old hypothesis. It's a beacon for quantum innovation. Near the quantum critical point of this transition, systems naturally cradle quantum squeeze states, where noise dwindles dramatically, sharpening measurement precision. A boon for quantum sensors and computing. Sohail Dasgupta, a graduate student under Caden Hazard, Associate Professor of Physics and Astronomy at Rice, crafted a theoretical model for the SRPT, refining a framework by collaborator Motoaki Bamba, a professor at Yokohama National University. Motoaki laid the mathematical groundwork, but we tailored it to the crystal's unique magnetic traits. When theory and experiment align, rare as a comet's passing, it's a scientist's greatest thrill. This bridges quantum optics with solid materials, offering fresh ways to sculpt and steer matter's phases using cavity quantum electrodynamics. The crystal studied is but one of a vast family of materials, suggesting a treasure trove of quantum phenomena awaits exploration in others with intertwined magnetic components. Demonstrating an SRPT driven solely by coupling two internal matter fluctuations marks a seismic shift in quantum physics. It establishes a new lens for probing and harnessing intrinsic quantum interactions within materials. The research, supported by the U.S. Army Research Office, the Gordon and Betty Moore Foundation, the Robert A. Welch Foundation, the W.M. Keck Foundation, the Global Institute for Materials Research Tohoku University, the National Science Foundation, the Japan Society for the Promotion of Science, the Research Foundation for Optoscience and Technology, the U.S. Department of Energy, and the National Science Foundation of China, stands as a testament to collaborative ingenuity. The content reflects the author's views, not necessarily those of the funding bodies.